very good evening to all of you. So today we'll be uh, looking at a new topic, which is anomaly detection. You are already familiar with the method of outlier detection, right? So anomaly is nothing but an outlier. So you are already familiar with one such technique wherein um, you learned how to detect outlier in one single variable. So um, the method was based on IQR or interquartile range, right? Um, so for any feature, we can have a 5 number summary, right? So uh, we'll have the minimum, and then we'll have the Q1, then the median, then the Q3, and then the max value. So this is the summary that we can have for any column or any feature or any data set or one particular variable, right? So we can have all these 5 numbers, which more or less define the distribution of the data in that column, right? And this is also pictorially captured in the box plot, right? So if you remember the box plot, you have a box wherein you have the Q1, median, and the Q3, and on the either sides you have the minimum value and the maximum value, right? Um, the outlier detection method based on IQR was you took uh, a value, right? So if the value is uh, uh, less than 1.5 times the IQR, right? So then you would so Q1 minus 1.5 times the IQR. You can take that as the lower limit for detecting outliers, and Q3 plus 1.5 times the IQR. This you can set as the upper limit, right? So you know this particular method wherein it is helpful for you to know evaluate as to which all numbers can be considered as outliers in a particular variable. Now, today we'll be learning one more algorithm. So there are many algorithms for anomaly detection. So today we'll be learning one such algorithm, and the IQR method is valid only for one variable, right? So you could find the anomaly in one particular variable, right? So you are given, let's say, a feature, okay? You want to find the anomalies in this feature, you can do that. But let's say someone gives you a whole data set wherein there are multiple columns, right? And then you want to detect anomalies, right? How will you do, right? So we'll approach multivariate anomaly detection today, but first we'll start with univariate because that is easy to understand. But the inherent concept of anomalies are the same, or outliers are the same, right? So there are two basic assumptions when we talk of anomaly detection techniques. So all the anomaly detection techniques work based on two assumptions. So the first assumption is that anomalies only occur very rarely in the data. So it will be small in number than the normal observations. Okay, so whatever is not an anomaly, I'll call that as a normal observation. Okay, so anomalies will always be rare, as in they will be less in number than the normal observations. So this is an inherent assumption of many anomaly detection algorithms. Okay, uh, and second one is obvious. So their features differ from the normal instances significantly, right? So whatever will be an anomaly will have a very wide, you know, range of features. As in, it will be you can clearly see it that no, this does not make sense, right? This does not belong to the data, right? Something like that. So um, yeah, okay, so this is anomaly detection. Two basic assumptions. One is the rarity of such samples in the dataset. Second one is that it will look abnormal. Their features will be different from the normal instances. Now, to give you a context of where and how we'll be using anomaly detection techniques, right? Um, so just think of scenarios, right? You have worked on the credit card fraud detection data set, right? So if you remember, you had variables which are, which were named as V1 till V29. So you had those 29 features, and then you had a target variable which said that whether that transaction is fraudulent or not. So this is the data set that you have worked with already, right? So credit card fraud detection, wherein each row means one transaction. So V1 till V9 are the features of one particular transaction, and based on that you had a supervised label which is the target, which was 0 or 1, right? So this was a supervised problem, right? And this was an imbalanced supervised problem, as in the number of fraudulent cases will be rare. Okay, so you can think of a technique wherein, let's say, I don't have the labels. Okay, I don't have the labels zeros and ones. So in that data set, if you remember, zeros are the numbers which depict that the transaction is valid, and one are the numbers which depict whether the transaction is fraudulent, right? So this was the target variable that you wanted to predict, and you used various techniques to handle imbalance in the data set, because you saw, there was only 0.2%, maybe the fraudulent cases were only 0.2% of the whole data set, right? So it was a very challenging task to predict the from a uh, in a imbalanced data set. It's very difficult to predict. uh, you know uh, you have to use all those techniques like oversampling, undersampling and stuff like that to come up with a model which would accurately work. Okay, but think of a scenario wherein, let's say, the labels are not there. Okay, how do you generate labels? So labels are something which from beforehand, right? So you know that this transaction is valid, this transaction is fraudulent. So someone has tagged across each transaction the labels, right? Let's say the company is fairly new, right? So the tagging has not happened yet. So no one has yet detected any fraudulent transaction, so the tagging has not happened. Okay, so there are no labels, right? Now you are said that, okay, just look at the features and tell me which all are fraudulent ones. Just look at the x's, right? X variables, that is the independent variables, and tell me which rows signify fraudulent transactions, right? So what will be your approach? Your approach will be definitely, you'll start looking for anomalies, right? So you'll start comparing. So you look at the whole data set, you'll see which values do not make sense, which values are different from all the others, right? Some variable will be very high, some variable will be very low in terms of values, right? And you'll start looking from that lens, right? So you'll start looking for anomalies, and that is how you will find fraudulent ones, right? Because this is the inherent assumption that you are making, right? So you know that these will be different from all the others, and these will be rare, right? So these fraudulent transactions will be rare in the whole data set, right? You will not find it frequently. So then you start looking at it from that lens, that okay, I need to find the ones which are, do not look like the others. Okay, so okay, so now that you get a sense of why this is an unsupervised algorithm, right? It's an unsupervised technique, because now we are not using the labels, right? So remove the labels. Just looking at the axis, can I find some patterns or some information which shows that some observations are do not belong to the overall distribution, right? So that is why it's a unsupervised technique, and these are the two inherent assumptions. The anomalies will be there, and the features will look different from the normal observations. Okay. So here, if you look at it that way, right? So let's say there is only one X, okay? Then the problem is fairly simple, okay? So what you are doing essentially is you have just one feature, so you can just use the IQR method itself or any such method, and it's fairly simple, right? So you don't have to use much of your knowledge. It's basically a simple rule-based thing that you need to use to detect anomalies. You will just look for very high values or very low values, right? But if you have that entire data set, right, and you want to detect anomalies, uh, so here you will be considering all the variables together to find out uh, a particular row which is the anomalous one, right? So just to set a context, right? So let's say in the credit card example, you have two independent features. Okay, so one is the amount of that transaction. Okay, and another one is the let's say the number of transactions that have happened. Okay, in that day of the transaction. Okay, so these are my two features. Let's say so one feature is the amount of that transaction, and the other feature is the number of transactions that have happened on that day. Okay. Okay, now let's say you are using just one feature to detect whether it is fraudulent or not, let's say. Okay, so there will be all sort of amounts of transactions, right? There will be varied amounts of transactions. Okay, uh, let's say there is one transaction. So you, if you just look at one variable, which is the amount, right? So there can be low value transactions, there can be high value transactions, right? You cannot say that, okay, the high value transactions are the fraudulent ones. You cannot say that, right? Because transaction can be of any amount, okay? So that's why just looking at the anomalies in one variable will not help us in finding anomalies, right? So maybe one transaction is very large, right? That is definitely an anomaly in mathematical terms for this particular variable, but maybe that is not the fraudulent one, right? So then let's say I took at look at the other feature, which is the number of transactions. Okay, so let's say I am seeing a small amount small amount transaction, but I am seeing very those transactions are very high in number, right? Let's say some person is just transferring 1,000 rupees, and the number of transactions happening on that day is 2,000. Let's say same value transaction happening 2,000 times. Okay, so just think about this case, right? So 1,000 rupees in itself is fine, right? So it's fine, and uh, but if it is happening again and again, so there are 2,000 transactions, that is kind of anomaly, because generally normal people will not send the same amount multiple times to some other account, right? So this is kind of an anomaly to me, right? This is how I can say that based on these two features together, I can say that, okay, this looks like an anomaly. But independently, if I look at both the features independently, probably I will not be able to say, because 2,000 transactions can happen. It can be a shopkeeper who is doing small, big, or medium transactions, multiple times, and very high amount of transaction, that is also okay. But if you see this combination, that one is medium and the other is very high, right? So then this combination itself seems like an anomalous case, right? So this is the inherent context that I wanted to set for multivariate anomaly detection. Okay, so in one variable, mathematically you can use some technique to get the highest and the lowest values, right, which will be classified as flagged as anomalies, right? But when it comes to multiple variables, right, or you have 20, 30 variables, think of 20, 30 variables, based on the whole data set you want to detect anomalies. Okay, so in that case, that leads to mathematical complexities, and that leads to uh, the birth of many advanced algorithms which will help you in detecting anomalies in the overall data set, right? It will be, so the detection will be based on the combined nature of the entire row as compared to the combined nature of the other rows in the data set. Okay, so I hope uh, the context of multivariate anomaly detection is clear, right? So why do we need it? Okay, because most of the situations you will be using this, right? So based on one variable does not make sense. Okay, so now let's look at the code part of it. Okay, and we'll be seeing one such algorithm which is isolation forest. I'll be seeing that today. So today I have taken a data set of a superstore. Okay, so there are two columns, okay, which are of particular importance to us today, that we'll be analyzing. So one is the sales column, another one is the profit column. So it's basically a orders data set. Okay, so in this data set I have the order ID, so each row corresponds to one order. Okay, so we have the order date, order ID, ship date, ship mode, customer ID, customer name. All of these things are there. What is the product that he bought? Okay, all sort of things are there. Uh, and here today we are particularly focused on two variables, which is sales and the profit. Okay, want to detect anomalies in these two columns. Okay, so. Uh, so let's first see if we are able to look at some of the anomalies or not. Okay, so I just did a df.sales describe, so I can see that the minimum value is 0.44, a median is somewhere around 54.49. Okay, 75 percentile is 200, around 210, and max value is very large, it's 22,638. So this is definitely an anomaly, right? So this max value does not you know fit to the distribution of the whole thing. So if I see the distribution of this sales column, I can see that there are a lot of observations in the higher range, right? So we will first look at the anomalies of in a univariate manner. So in case of sales only, you can say definitely that these observations, right, are anomalies, right? So these observations which have very high values, these seem to be anomalies, right? So now if I plot the distribution again, okay, in doing just a dist plot of the sales. So here you can see that it has a very long right tail, right? So the tail is huge. We have many observations which do not comply to the actual majority distribution, right? So these are probably the anomalies. So we'll try to find them out. So if I just calculate the skewness of this data set, so it comes out to be around 12.9, which is positive value. So this is a positively skewed data set, right? If you remember the skewness uh, definition, right? So if it has a very long tail on the right side, it's said to be positively skewed, right? And if you calculate the skewness value of this distribution, it will be positive. Okay, so simple way to remember uh, whether something is positively skewed or negatively skewed, right? So just look at the tail. So if the tail is in the right side, that is it's a right skewed distribution, or it's a positively skewed distribution, right? Because the tail is in the positive side, the long tail is in the positive side, so it's a positively skewed distribution. Okay, but if the tail is on the left hand side, right, then it's a negatively skewed distribution because the tail is in the negative side. Okay, so one more property of a distribution which we did not talk about is the kurtosis. Okay, not relevant here, but just because mean, the standard deviation, the skewness, right? So these three are the properties that you know of. So mean is the first order moment, we call as the first order moment. So it describes the centeredness of the distribution. Where is the distribution centered at? Second is the uh, standard deviation or the variance, right? So variance is called the second order moment. So it basically gives you the spread of the data. Okay, so these are important aspects of a distribution. So one is where the distribution is centered at, where is it located at. Second one is the variance, which says you how much spread out is the data, right? Third one is the skewness, which is the third order moment, right? And that gives you in which direction is it skewed, right? If it's symmetric, then you will have a skewness value of 0. So skewness is also one of the properties of a distribution, which gives you how in which direction the tail is of the distribution. Okay, and then the fourth order moment is the kurtosis, which gives you how uh, you know it gives you a measure of the pickedness of the distribution, right? So just to give you a sense, so this will have a high kurtosis value than this distribution, because the peak is more pointed. So the more pointy it is, so uh, so the more pointy the distribution is, more will be its kurtosis. So this will have a very high kurtosis as compared to something like this. Okay, because this is more pointy, right? So how pointy is the distribution, that is given by kurtosis. Okay, so it's basically depicting peakedness, uh, how severe the peak value is, right? So the maximum value is occurring how many times, right? So that is that. Okay, so okay, so just this was just out of context, I gave you the definition of kurtosis. So here we can see that the distribution is positively skewed. So that means in this side we will have outliers, right? So in this segment we'll have outliers. Okay, so let's analyze the profit variable. So this was the sales variable. So what for every order, what is the amount of sale that has happened? So that was this variable. Okay, and for every order, what is the profit that the store made? That is this variable. So we'll see this variable now. Okay, so here we can see that the profit has a minimum value of minus 7,000, which is seems like an outlier, right? Uh, and the maximum value is also very deviant from the overall data distribution. Okay, so here if I just plot it right in a sorted manner, okay, I can see that I have outliers on both sides, right? So here probably these values are kind of outliers. Here also probably these values are kind of outliers. This is definitely an outlier, right? With respect to this variable only. Okay, so I'm not saying that this you know in this data set this row will be an anomaly. I'm not saying that. With respect to this distribution, I can say that these are anomalies, right? But I cannot say that the order was fake or the order was fraudulent. This type of conclusion I cannot make. I can just talk in mathematical terms with respect to this variable. Okay, that these are outliers, right? So it can happen, right? So in some product you can have a loss of minus loss of 7,000 rupees, right? Of course, this is not in rupees, but yeah, so you can, in whatever units it is, you can have that kind of loss. It's not theoretically impossible, right? So yeah, so we have outlier on both sides of this profit distribution. Okay, if I see the distribution, plot the distribution, I can see that I have a tail on both sides, right? And if I calculate the skewness here, I'm getting 7.56, which shows that it's a positively skewed thing. But yeah, so you will probably say that it looks like a symmetric one, right? But it's just that the positive tail is more dominant than the negative one, right? So you can see this from here also, right? So there is just one observation which is skewing it, whereas there are many observations in this side which are skewing it. So the skewness is positive because the right tail is more dominant. Okay. Okay, so now we want to detect these anomalies, right? So we'll be using an algorithm today, which is called the isolation forest, right? So let's see, try to get an intuition of how this algorithm works and how does it help in detecting outliers. Okay. So let's draw a box plot. Okay. So in a box plot, what did you have? So you have this kind of a distribution. So this is a normal box plot wherein you have a normally distributed thing, and this will be your minimum value, maximum value. This will be your Q1, Q2, and Q3. Basically, this is the median and so on, right? So this is how your box plot looks like. So you had this rule that from Q1, I will measure 1.5 times this side. So you'll probably set a value, somewhere around here. You'll probably set a value somewhere around there to say that this particular thing is an outlier. So beyond this, in this region, whatever will come, I will call that as outliers. So you can set this value. So this is nothing but Q1 minus 1.5 IQR. Okay. And similarly, you can set it here as well, right? So this is uh, Q3 plus 1.5 times IQR. Okay, so these are the two values. You will say that beyond these values, whatever values come here are my outliers. Okay, so this is how you detected outliers, right? So this is how you detected very less and very high values, right? In a particular given variable, right? So you just calculate all of these Q1, Q2, Q3, median, minimum, maximum, and then you applied this rule to detect outliers. Okay, so now uh, what happens in isolation forest is that here also you want to detect some lower values, so extreme lower values and extreme high values. Okay, so this is a tree based algorithm, so we will be constructing trees as well in this algorithm. So you learned about how trees work, right? In your supervised learning classes, in your decision tree classes, right? So you learned how to construct trees. But here the trees are quite simple. It's not that complicated as we saw earlier. So there we used to split based on some, it was hinged on some dependent variable, right? So whatever is explaining my dependent variables the most, I used to split on that, right? In random forest or in normal decision tree also, right? So I calculated entropy, took the difference of it, calculated information gain, whichever feature is giving me most information, I will split on that. So all of that complexity was there. Here the tree is fairly simple. Okay, so I'll just explain how that is constructed. So what we will do is that here we will take one feature randomly. So we'll not do any entropy Gini calculation. We'll take one feature randomly, okay, from the data set. In case of univariate, you just have one feature, so that feature will be selected. Okay. So then what I do is that I split that feature in two parts based on a random value between the minimum and the maximum. Okay. So just to give you a context, so let's say I have this data set. I have 5 numbers. So this is my X. Okay. So I have 5 numbers, let's say. So clearly 100 is my anomaly here. Okay. I have 1, 2, 3, and 4. So these are my normal numbers, seems like normal. And 100 is clearly my anomaly here. Okay. So let's say I want to detect 100 through this isolation forest. So how do I construct a tree here? So here what I do is I pick a random variable, I pick a variable randomly or a feature randomly. So here since I have only one X, so I'll pick this. Okay. Then what I do is that I take the minimum and the maximum value. So minimum is 1, maximum is 100. So in between these two values, I select any value in between. Okay. So let's say I selected 60. Okay. So now my split will be, so in the root node, my split will be X less than 60, and so X less than 60 is my split. So less than 60 will come here in one branch, and more than 60 will come in another branch. Okay. So here let's say X less than 60 is my rule of the first root node. Okay. So what will happen is that from here I will get uh, you know certain two divisions. So let's say here I had uh, five observations right here. So I put this rule. What will happen? 4 of them will go here and 1 will go here. Okay. So you see, since I have taken a very simple example, uh, I have already done my anomaly detection if you see it that way, right? So I am already able to figure out which variable is anomalous, right? It's a very simple, for very simplistic understanding. First try to understand it, what is happening, right? So this anomaly got segregated in the very first node itself. Okay. This anomaly got segregated in the very first node itself. Okay. Now you repeat this process, let's say, till you go till a certain depth, right? Or till you classify all the observations one by one. Okay. So here I had 4 observations, 1, 2, 4. Here again, let's say I pick 1 as the minimum value, 4 as the maximum value, right? Here in this node. So let's say I take any split, any random split. So let's say X less than 2. Okay. So what will happen? One observation will go here and 3 observations will go here. Okay. Right. So this is how it is happening. Okay. So and so on, right? So we will go till each node has only one observation. We'll go till that depth. Okay. So we'll not restrict our tree. So we'll move on till we get you know uh, to a point wherein each of the leaf nodes have one value. Okay. So what is the advantage now? So now how do I detect anomalies? So I will say that the observation, right, which went to went in more depth in the tree are my normal observations, but the ones which got segregated at the top, right, which have low depth, those are my anomalous observations. Okay. So how can I say that? So here I segregated one, then again I will construct a tree, right, and so on. So I will have all sort of things. But if you just look at this observation, it got isolated in the very beginning itself. Okay, so that's why the name isolation forest. So we are isolating the anomalies. Okay, so which observation got isolated in the at the very beginning, right? So that is what will be considered as anomalous. So this variable is this observation is anomalous as compared to the ones which have gone to more depth, because this got isolated in the very beginning. And just think of this, just think of the power of this algorithm. So if you have uh, you have a very high value in the end, right? So let's say you have one outlier which has the maximum value, it is very high. Okay, what will then happen is that in between those two values, it will just get uh, in between those two values, if you take a split in between those, the minimum and the maximum, there is a very high chance that the split will come somewhere in between, and on the other side of the split, the anomalies will be out isolated, right? And you understand the logic, right? So here we will basically give a score based on the depth in which that observation got segregated. Okay, so based on the uh, we will construct a tree, and based on the depth we will give them a score, right? Which will be called as, let's say, the anomaly score. So uh, this guy's score will be high in terms of the probability of this being an anomaly will be very high, because it got segregated at the very top. Okay, whereas these observations, right, these will go to more depth because these are normal observations. Okay, so you saw, I hope you have developed an intuition of how depth can give us a measure. Depth in the tree can give us a measure of whether it is an anomaly or not, or what is the probability that it will be an anomaly, right? Based on the depth in the tree. Okay. So normal observations will go further in the tree, but anomalous ones will get segregated at the top itself. Okay. So isolation forest is basically that, right? So this I gave you an example of one variable. So what happens in isolation forest is that you have this entire data set, okay, x1, x2, x3, x4, and so on. It will randomly pick one feature, okay, and then it will take the minimum and the maximum value and split in between. Okay, so then these two branches will come up. Then again it will pick another feature, and then it will again construct a tree, and so on. So construct a node, right? So and so on. So this will continue, right? So the only difference here is that in case of normal decision trees, we used a lot of mathematics, entropy, and Gini to come up with the information gain, and based on that we split. Here we are just doing random splits, right? And random splits are just enough to give us a sense of which all observations got split, got isolated in the very beginning itself. So basically, based on the depth in which our observation landed finally, right? In which level did it land? That gives you a sense of how normal or abnormal or anomalous the observation is, right? So the depth will give you that perspective. Yeah, so Yagnik says that if condition x, if condition, so because you are splitting on random values, right? You are splitting based on random values, right? So you took 1 and 100, then you got a random value 60, and then you split it that way, right? So Yagnik says that what if the random value comes up to be 4? So x less than 4 would be my first split, x greater than 4 would be my x greater than equal to 4 will go here. So what will happen is that uh, 4 and 100 will come in this bucket, 1, 2, and 3 will come in this bucket, right? So think about another split on this particular node, 4 and 100. This time 100 got split, right? But unfortunately 4 came there in that part, because you know, between 1 and 100 getting a number 4 is very unlikely, right? You are, most of the times you will get a value, you know, greater than 4, or you know, greater than 10, right? So you have a 90% probability of getting a number greater than 10, right, between 1 and 100. So it's a very rare case, but I understand where you are coming from. So to tackle for this, we use the forest, right? We just don't use a one tree. So in one tree it might happen that way, right? We cannot do much. But let's say you take 100 such trees, and you calculate the average depth of a particular observation in each of the trees, you will land up with a score which gives you a much better sense of whether it is an anomaly or not, right? And that's why we use a forest, okay, and not just one tree to make the decision. Okay, so now so I hope the isolation forest algorithms working is clear. So this is what is written. Isolation forest is a tree based model. In these trees, partitions are created by first randomly selecting a feature, and then selecting a random split value between the minimum and maximum value of the selected feature. Okay, and basically the depth basically gives you uh, the notion of how anomalous the observation is. Okay, so in sklearn we have this in sklearn.ensemble we have this algorithm, isolation forest, which we will be using. So we don't need to construct trees by ourselves, so it's already there. And what this algorithm gives as output is interesting, right? So uh, of course, if you want it to predict the anomalies directly, it will do a prediction, okay, directly, that these are anomalies. But the inherent working of this algorithm is based on the depth of the tree, right? So there is some calculation of depth based on, there is some complex formula which, you know, gives you a score, which is basically called as the anomaly score, right? And this isolation forest implementation in sklearn library has so it gives you a score between minus zero point 0.5 to zero point 0.5. Okay, so just remember this part. Okay, so here what happens is that it gives you a score between minus zero point 0.5 and zero point 0.5, this isolation forest. And this is the whole range. And anomalies are basically values which come in this side. Okay, so this part is anomaly, and these are normal. Okay, so these are normal. Okay, so it gives you a range of scores for each particular row in the data set. And uh, basically negative values you know, are kind of anomalous. Okay, so this is what this isolation forest gives. Okay, and it will also predict labels as well directly, right? So from here, if you get the score, you have to decide on your own as to what threshold you will keep to decide the anomalies. So will you say that these are anomalies, or will you say that these are anomalies? So you have to decide this threshold by yourself. But you know, isolation forest directly gives you the predictions of whether it is anomaly or not, binary, right? So it gives you a score. So the dot fit, so basically the dot predict will give you a score of minus 1 and 1. So 1 are the normal cases, and minus 1 are the anomalies. So these are the anomalies, and these are the normal cases. So yeah. So this is how the isolation forest works. So basically nothing, it's nothing but a dot fit dot predict. So you get all the x's, you pass it to dot fit, right? It will do all of that detection, and then you pass the x, overall x again. It will give you the anomalies in that x, right? So pretty straightforward. So let's see the implementation. So first we will start with a univariate one. So we'll just pass one variable. Okay. So I have initiated one instance isolation forest. I have put n estimators and contamination, two parameters. So okay, so here is the interesting part. N estimators, you know, right? So this is the nothing but the number of trees that you want it to construct. Okay. What is contamination? So basically, it is asking you what is your guess of the number of the percentage of anomalies in this data set. Okay, so it is asking you. So no, how many anomalies uh, are you looking for in this data set, right? So uh, 0.01 means that I said it that there are 1% anomalies in this entire data set. Okay, so that is basically the parameter contamination. Okay, so what is the number of what is the number of anomalous, what is the percentage of anomalous points that you expect in this data set. Okay, why does it need this value? So as I suggested, right, so this gives you an anomaly score, right? But once you rank the anomaly scores from, you know, in the ascending order, so you will have all those negative values coming at the top, and gradually you'll have the positive values. So at the top, whatever observations have negative values, those are your, you know, kind of anomalous ones, and all of the observations below are your good ones, right? So contamination is basically used to, while you are doing dot predict, right? Because then it has to decide, right, which one is the anomaly and which one is not. It can generate the score based on the depth of the tree and all, that is fine, right? But once it has to give a verdict that this is anomalous and this is not, at that point it uses this contamination, right? So let's say you have 100 data points in your data set, it will, and you gave the contamination parameter as 0.01. That means you are saying that there is out of 100 there is one anomaly. Okay, so what it will do is that it will get all that score, all those scores, it will rank them in ascending order and pick the top one and give it to you. So it will say that this top one is the anomaly because you wanted one anomaly, so this is the one. Okay, similarly, if you have, let's say, 1,000 observations, right, and you give 0.01 as the parameter, that means you are saying that there are 10 anomalies in this data set, right? 1% of 1,000 is 10, right? So you are saying that there are 10 anomalies. So all the 1,000 observations will have some scores attached with them, anomaly scores. It will rank all of them in ascending order and then pick the top 10 and give it to you, saying that these are anomalies, right? So we will see this. Okay, so um, this is how I initialized the isolation forest. Now I'm just doing a dot fit on the on one particular column. Okay, which is the sales column. Okay, and decision function is the method which returns the scores. Okay, so the anomaly score that I was talking about, right? So this, you can see it says average anomaly score of X of the base classifiers. The anomaly score of an input is computed as the mean anomaly score and so on and so forth. So this is the decision function which gives you the scores, right? So I have stored that in a variable called anomaly score univariate sales. Okay, now I am passing the uh, sales values. Okay, and then I have this another uh, yeah, so I'm passing this sales and getting the values of the anomaly scores, and then I'm storing it in a variable called anomaly score univariate sales. Okay, then I'm also doing this dot predict and passing the same x to get the values of the actual prediction, right? So whether it is anomaly or not, binary. Okay. So now I'm sorting this data frame in ascending order based on anomaly score invariant sales. Okay. So let's see what has happened. So basically I passed on this variable and I got these two variables corresponding to the uh, scores. Okay. So this was the highest score, I guess, right? So no, this was the highest one. So uh, it got a pretty high score, right? So almost uh, all of these got the same scores, right? So you can see um, these variables, right? These values got detected very well with this algorithm, right? So these have a very less anomaly score, which means that these are highly likely to be anomalies. And you can see the prediction is -1, which says that this is an anomaly, right? And you see all the other observations which are kind of in the tail of this data set when I'm sorting this in based on anomaly score. So let's say these values you see are around 0.38. So the range is from minus zero point 0.5 to zero point 0.5. So these are the normal observations that the model has detected, and for this the label that it has given is 1, right? And for anomalies it has given a label of -1. And how many -1 will be there? Can you guess how many number of -1s will be there? So it will be nothing but 0.01 into the number of uh, data points that are there in this data set, right? That many number of anomalies will be there. That many number of -1s will be there. Okay. So I hope this part is clear. So this is how we calculate the anomaly score uh, based on univariate, based on only one variable. In this case, only sales. Okay. So okay. So if I just plot the decision boundary as to what is the cutoff boundary that it has detected to classify anomalies. So you can see if the sales is exceeding somewhere around 2500, it is considering it as anomaly. Okay. So is it possible that one observation has a negative anomaly score and is labeled 1? Yeah, it is possible, right? So -1 and 1 is based on the contamination parameter, right? So let's say you say the model that there are no anomalies, so you give the contamination parameter as 0. So all of them will be considered as normal, right? But they will definitely have the scores with them, right? So that is the case. Okay. So you can see the decision boundary, right? So this is what the anomalies are based on this algorithm. So it has uh, detected these as anomalous ones. Okay, these observations greater than 2500. We can do a similar exercise on profit as well. Okay, so again same thing, right? And in the dot fit I am just passing on profit column, and then using the decision function to store the anomaly scores in this variable called anomaly score univariate profit. Okay. And I'm storing the predictions, that those -1s and 1s, in outlier univariate profit. Okay. So let's see how this looks like. So here you can see, so I had, based on sales, I had generated scores and the predictions, and based on profit as well, I can generate the based on profit as well. I have generated the anomaly scores and the corresponding predictions of whether it is an anomaly or not, right? So does it work on categorical variable? So since this is a tree-based algorithm, you will probably uh, of course it will not work with categorical variables, because this is inherently you want to come up with values which are not complying to the distribution. So anomalies inherently have this notion of continuous variables, right? Because in categories you cannot say that this category looks anomalous, right? Something like that. So yeah, probably it can be done, but uh, thinking straight, it does not make sense for a categorical variable. But mostly you'll be seeing this getting used in numerical features only, as in uh, continuous features only, right? Not discrete, not even discrete, right? So that's the thing. Okay. Of course, you can have no anomalous categories, but in a different context. Not cannot be done via a tree-based algorithm, because here you are splitting based on a particular value itself. So it isolation forest will expect you to give numerical values. So okay, so I got four. Uh, I got univariate analysis or univariate anomaly scores based on sales and profit separately, right? So you can understand. So what is this saying? So this score is saying that this is the anomaly score based on sales, and this is saying that based on sales, this value looks like a anomaly, right? Okay. So now in case of, so this is how the decision boundary looks in case of profit. Okay. So here what is happening is that uh, you will have on both, you have outliers on both sides, right? So this is the anomaly zone. So it has, classified, profit values less than -100 as anomalies and greater than 100 as also anomalies. So let's see which all variables are considered anomalies by both the algorithms, right? So you can do some analysis. Let me just run this kernel. So let's see which all rows are considered anomalies by both of the uh, which all are anomalies both in terms of profit as well as sales, right? So just trying to look at those examples. So there are a lot of anomalies which are, both anomalies in terms of profit as well as in terms of sales. So see, you have sales values which are high, and you have profit values which are very negative. So these are also, anomalous cases. Okay, so just want you to think of it, right? So what is happening in this case is that uh, an observation which with a very high profit, may not be a anomaly in the context of the domain, right? So there can be an order which has a very high profit, or there can be an order which has a very high loss. Okay, similar goes in terms of sales as well, right? There can be an observation which is, has a very high sale price, right? So the anomalous cases, if you want to see in terms of the superstore, or in terms of the domain, or in terms of the actual use case, probably you want to look for those values which are anomalous in terms of both these combined, right? Profit as well as sales, right? So the just think of an observation which has, very high sale amount, but the profit is very low. right? But profit is negative, right? Severely negative. Okay, in this case, this kind of raises suspicion that even though I sold at a very high price, then also I'm incurring some high losses. So these can be situations wherein which all could be anomalies in terms of the business, right? Maybe some anomalies would be if the profit is more than the amount of sales itself, right? So these type of anomalies could be there uh, in the data set, which we want to find out. So if you just take profit and sales separately and try to find out the outliers, that will not make sense. So you have to put both of these variables together and let the model decide based on these two variables together what all are the anomalies. Okay, so this is what we will do now. Okay, so we'll put both these variables together. So if I just plot the sales and the profit, okay, it has to show some kind of a linear trend which is kind of visible, but I can see a lot of anomalies here and there. Okay, so first I'm scaling it. Okay, so scaling the features, um, doing a dot fit transform and doing a min max transformation. Okay, so min max is nothing but it will convert all of the features to in the range of 0 to 1. Okay, so why I'm doing this is because I need these two variables in the same ballpark range. Okay, so because sales and profit will have some somewhat different scales, need to get both of them in the same scale. Okay, so that's why I did a min max scalar and did a dot fit transform to get my x's. Okay, so in this x I have two variables, sales and profit. Okay, so now I'm doing the same thing, right? So n estimators, contamination, and then when I do a dot fit, instead of one variable, I'm passing, x, which may have more than one variable, right? So this decision function and predict time is storing in multivariate anomaly score and multivariate outlier. Okay, and if I want to visualize how my classifications look like, right? So here I am plotting the anomalous and the normal ones with a different color. Okay, so sales and profit, right? So this is the plot that I'm making. Okay, and and you can see this chunk of brown values are the values which are normal values, and these values which are tagged as blue are the outliers. Okay, okay, so now let's say I have, so now I want to investigate and see some of the anomalies. Okay, so uh, let's try to see those anomalies which are classified in univariate as well as in the multivariate one. So let's say I see this chunk. So just look at this chunk, this subset of orders, which which is anomaly in terms of profit, sales, as well as in terms of multivariate. Okay, so which are these values? So let's try to see. So there are many such values, right? So seems like a whole data set is there which has this kind of value. So the profit amount is very low. Okay, the sales quantity is very high. This has been flagged anomaly with respect to sales, with respect to profit, as well as with respect to combination of both. Okay, So it would be interesting to see those observations which are not anomalies in terms of sales or in terms of profit, but they are anomalies in terms of the overall mixture of the two, right? So let's just do this. So this is I'm just taking uh, a subset which is normal according to sales, which is normal according to profit, but which is an outlier according to the multivariate, basically the combination of sales and profit. Okay, so let's just see if there is any such observation. Yeah, so there is one such observation, right? So you can see uh, the profit is decent, the sales amount is also decent, so these were not flagged as anomalies in terms of sales and profit independently, but in terms of the combination that was flagged as an anomaly. Okay, so you see the impact of these two, right? So impact of having both of them together into the model. Okay, so I think this is all about isolation forest and anomaly detection. Okay, uh, scaling before isolation forest. So see, there are many algorithms which require scaling, there are many algorithms which do not require scaling. um, Probably if you are going for algorithms wherein you are using gradient descent, like neural networks, or other algorithms which require you to minimize a loss function, right? In those cases, probably in those cases scaling is a very good is of much help, because it will help you reach the minima faster. Okay, so scaling has that capability. It will help you reach the minima faster. But in isolation forest, scaling is not that relevant. But to be on the safer side, you can scale your variables before doing any observation, before doing any any of your work, just to be on the safer side, right? So you cannot remember which algorithm requires scaling, which algorithm does not require scaling. So it's better if you scale and then proceed with the algorithm, right? So it's never a bad idea to do some scaling. Just as a rule of thumb, you just do scaling before applying to the algorithm. Of course, you can go into the depth of the algorithm and try to reason out why scaling would or would not be required. But as a safety measure, you can, if you are working on project, it's always better to scale the features before passing it to the algorithm.